Any question about the model so far? Is it too difficult for you? I think it's not that difficult, right? This is from the cavity. You have a constant loss, you have a delay, you have gain median, and the G in principle is a complex Lorentzian function, but if it remains complex Lorentzian, we cannot get analytic solution, right? A complex Lorentzian in the complex, you cannot combine the terms. So the only way we can do is approximate the complex Lorentzian into Taylor series, and only to the second order. If you have a cubic term, you will have something extra, which is no longer Gaussian. If it's no longer Gaussian, we cannot have steady-state solution. Okay, so that's why we only restrict ourselves to second-order approximation. And if you do that, each term, you have 3 terms, right? Constant term, linear term, quadratic term. Each term is meaningful. Const term gives you overall amplification. Linear term gives you extra delay due to the gain median. Quadratic term contributes to a Gaussian function which can be combined with the original Gaussian function. You got a new Gaussian, a new bandwidth. Still a Gaussian, but new bandwidth. Okay, that's it. Okay. So the gain median contributes to actually most important of all 2 effects: spectral filtering or gain narrowing and the delay increment. So let's focus on these 2 terms. Spectral filtering comes from the combination of the 2 terms, as I mentioned here. After combination, you have a single Gaussian, but it comes from combination of this one and this one, okay? And that's why you have this formula. 1 over gamma prime. Gamma prime is the new post-width parameter, equals 1 over gamma. Gamma is the original post-width parameter, plus modification term, which is 16g over omega g squared. Okay? So you can get this approximation. New parameter gamma prime is roughly equal to old parameter gamma minus a positive number, 16g gamma squared over omega g squared. So it means gamma prime is always less than gamma, smaller than gamma. But previously, we have known the bandwidth formula is proportional to square root of gamma. So if your gamma becomes smaller, that means your bandwidth is reduced. So after the gain median, your spectrum becomes narrower. Okay? Is it good or bad for post formation, in your opinion? If your spectrum becomes narrower, is good or bad? Bad, because you need the broad bandwidth to have a short pulse. So actually, gain median is negative, although it provides extra power, right? But it sacrifices your post duration potential. The second contribution from the gain median is delay increment, okay? And as we know from the previous page, it comes from here, imaginary part of your gain spectral coefficient, right? Why it's about imaginary part? Let's go back. Because delta t comes from the second term. Because of j, this is a purely imaginary term, right? So g imaginary part is here. The first and the third terms are about the real part. only the second term is about imaginary part. So imaginary part of G contributes to delta t. Okay? And we have already plot the imaginary part curve, the red one, before. But this is from complex Lorentzian model without any approximation. So what happens when we perform Taylor series approximation? For the real part, we have Gaussian function, right? For the imaginary part, actually, we use a linear function with negative slope around the central frequency for approximation. And based on the Fourier series property, a Fourier transform property, we know a linear phase modulation in the frequency domain means a delay in the time domain. So actually, the slope determines the delay, the extra delay or delay increment. And what is the slope of this red curve? You can easily calculate it's minus 2g over omega g. So that's why your delay increment is exactly 2g over omega g, just the absolute value of this slope. And negative slope means extra delay. If you have a positive slope, it means reduce the delay. Delta t is negative. Okay? 好，所以事情其实也很简单嘛。这两个 curve 本来是 complex Lorentzian， 我做了泰勒展开近似之后，这一个部分实部被近似成高斯，那这个虚部的部分被近似成线性。好，那近似成高斯，最后我会有第一项 spectral filtering。虚部近似成斜直线，我会有 delay increment， 就是这样来的。OK。Okay, now we have one element to be analyzed, the modulator, but the intensity modulator is better modeled in the time domain instead of frequency domain. So we have to perform inverse Fourier transform for the spectrum we obtained to this point. Okay, so the spectrum is big A prime. We need to calculate its time domain representation, small a prime t, but remember, prime here does not mean time derivative. It means something else. Okay? It's inverse transform of big A prime, and the big A prime is approximated by a Gaussian function, so you can easily calculate its inverse transform. It will be another Gaussian function. Okay, so this is the result. You can see. Neglecting the amplitude, this is a Gaussian. And the central point is shifted to round-trip time, which is the summation of cold cavity round-trip time and the delay increment due to the gap median. So together it means hot cavity round-trip time. Hot means with gap median. Cold means without gap median. So this is the actual round-trip time in your laser cavity. Because your cavity is lasing, TR has to take into these two terms account. Okay. So for the purpose of illustration, this is your initial assumption. Time domain is a Gaussian. Frequency domain is also a Gaussian. Both are real functions. After cavity at the gap median, you got a new spectrum as we analyzed before. You have a narrower spectrum. You have a tilted phase. You might have taller spectral magnitude. And before analyzing the contribution due to intensity modulator, you need inverse Fourier transform from frequency domain back to the time domain. So this is your time domain representation of the same pulse. Okay. The next thing is we need to calculate what happens. This is your new input pulse, and what is the new output pulse. Okay. Okay, low modulator effect So this is the typical model. The impact of an intensity modulator is modeled by a transmission function of electric field. Eta of t is exponential to the, this is exponent, minus delta m times 1 minus cosine omega mt parentheses. And this is the corresponding transmission curve of this model. There are two parameters. The first one is delta m here. Okay, what is delta m? It's associated with the modulation depths, as I indicated here. Okay, this is total transmission, totally transparent, and the minima transmission is e to the minus 2 delta m, and the distance means your modulation depths. The larger the distance, that means a stronger modulation can be provided by this modulator. Okay, and since the minima transmission is related to e to the minus 2 delta m, so delta m is referred to modulation depth parameter related to modulation depths. The second parameter is omega m, shown here. This is modulation frequency related to modulation period Tm in this way, 2 pi over Tm. And this is the peak-to-peak spacing in the time axis is your modulation period. Okay? So in this model, we only need to focus on delta m and omega m. One is about modulation depth, the vertical direction. The other is modulation frequency or period, the horizontal axis. Okay. But the previous model is not good for our purpose because we always need Gaussian, okay, to get a steady state solution. So we need approximation again. Say if the pulse width in steady state is much narrower than the modulation period, just like this figure. The blue solid curve means your transmission function as shown in the previous slide. Spacing is modulation period or round trip period. And the bottom one is the steady state pulse. If the steady state pulse, the width is much narrower than the period, which is usually true. Why? Because if it is violated, there is no active mode locking, right? 如果我到了 steady state， 我这个脉冲宽跟这个 TR 也差不多，就没有主动锁膜，你直接把调变器放到腔外就得到 TR 的宽度，不是吗？对不对？我们就是为了制造比 TR 窄很多的 pulse， 我才把它摆到腔内，所以合理。这个 in general, the width has to be much narrower than TR. So this assumption is usually true. So if it is true, what happens? This is the original model. And if this is true, you can simplify cosine omega mt by, again, second order Taylor series. Cosine omega mt is close to constant 1. There is no linear term, but you have quadratic term, minus 1 over 2 omega m squared t squared. And this is true if your phase, omega m times t, the absolute value is much less than 1, guaranteed by this relation, this assumption. Okay? So if you replace cosine omega mt by 1 minus 1 over 2 quadratic function, 1 minus 1 will cancel with each other. So you got a Gaussian function again. Okay? And when you see Gaussian, you should be happy because now everything is Gaussian. Okay? So we need this assumption. And this is illustration. If you use this model, that means the blue solid curve is replaced by the red dashed curve. which is a good approximation over the central region. If your pulse width is quite narrow, this is a very reasonable assumption. Now, go back to mathematics. The pulse as the output of the modulator in the time domain is denoted by A double prime of t. A double prime does not mean second order time derivative. It's just a new pulse, which is the input pulse A prime of t times your transmission function eta of t. A prime has been derived before, so this is a copy. Eta of t, remember the Gaussian approximation in the previous slide, is repeated here. Okay, so it's a very easy mathematics. You can simplify because the first term is a constant only. The second and the last terms are both Gaussian functions. So their product still a Gaussian function. Of course, you have a new pulse width parameter. So you just combine the last two terms together. You got a new pulse width parameter gamma double prime. Okay? Where gamma double prime is related to gamma prime by a modification term, delta m, omega m squared over 2. Okay. So by illustration, this is the output from the cavity and the gain medium, which is A prime. After the modulator, you got A double prime. What's the difference? You can see the peak is the same, but the width is narrower, right? Think about the contribution from the modulator is here. What is the peak transmission? 1. So that means peak will not be changed, right? When t equals tr, this term is 1. You have maximum transmission, 100% transmission. So peak is preserved. But because of the extra Gaussian, after multiplication, you got a narrower width. So the output A double prime is narrower compared with the input A prime. Okay? Okay, so we have completed step 2. We can move on to step 3, steady state equations. The pulse envelope must reproduce itself after one round trip, except for one thing. You can have a delay TR. TR does not have to be 0 because it takes time for a pulse to circulate inside the cavity once. Okay? So basically, A double prime should have the same shape as A, although the center can be away from A by TR. Okay? So this is the equation you can have if you want to solve the steady state pulse. A double prime equals A of t minus TR. You can have a time delay, but everything else should be the same. So if you use the A double prime formula from the previous slide, which is here, and the A from the first slide is here, you can equalize these two. Okay? So this is the equation you can have by the steady state analysis. Okay? But it looks like we have one equation only, but how many unknowns do we have? From the very first slide, we know there are two unknowns. Steady state pulse width, steady state amplitude. But you have only one equation. You have two unknowns. It seems not promising, right? But in reality, you have two equations. Where? You can equalize the amplitude, E0 and E0 times the other two terms. E0 can cancel with each other, so you got equation 1. Besides, gamma double prime has to be the same as gamma. You have equation 2. Okay, you have two equations actually. you have two algebraic equations. Although this is one equation, but this is not algebraic equation. 这是两个函数的相等，这不是一个代数方程，它其实蕴含了两条代数方程。Okay, so it's possible you can have unique solutions for the two unknowns. Right? But if you are very picky, you might feel something wrong because E0 has been cancelled with each other. No E0 anymore, right? But E0 is one of our unknowns. What is E0? The steady state pulse amplitude. Supposedly we need an equation about E0, but E0 has cancelled with each other. Will that be a problem? No problem, but why? We have to look further. So we have algebraic equations 1 and 2. They can be simplified for solving the two unknowns. But these are the two intermediate unknowns, not final unknowns. Gamma and G, analytically, okay? So by equation 1, this is your equation 1. This one equals to 1. But we have already derived the formula about gamma prime before, so use it here. Okay? And the simplification, you got this one. And it is equal to 1. Say this is new equation, 1 prime. The second equation, gamma double prime. But we have derived the formula about gamma double prime before. So just use it. Gamma prime plus modification term equals gamma. So after some gamma cancel with each with gamma, so you got this equation 2 prime. Okay, so you have these two equations. And in these two equations, 1 prime and the 2 prime, big gamma and the small g are two unknowns. So you can solve them uniquely in principle. But if you do so, we still have no idea about the final answers, right? We are most interested in steady state pulse width, delta t, and the steady state amplitude, E0. So what are the relations between delta t, E0, and the gamma and the g? That's the central issue, right? But this is what you have from the Gaussian model, right? Steady state pulse width is determined by square root of constant 2 log 2 over gamma. So if you solve gamma, you can directly calculate delta t. So there is no problem. The more complicated thing comes from the second unknown, E0. As I indicated earlier, E0 seems to be cancelled with each other, but no worry, here is the answer. E0 is related to peak intensity in this way. This is from lesson 1, the pointing theory, right? And you can also replace peak intensity by average intensity times the amplification factor, which is TR over delta T, which is also from lesson 1. Remember, the peak power is the average power times amplification factor about repetition period over a single pulse duration. Okay? And there is a pulse shape factor, which is used in replacing factor 2 by factor 1.88. 因为是高斯，所以你有一个脉冲形状的修正项，会让2变成 1.88. Okay? Then your average intensity is governed by a formula also introduced in lesson 1, review about CW lasers. Average intensity is the unit intensity times G max over G minus 1 times tau GW. W is pump rate. Tau G is the lifetime of your gain medium. These are the parameters you have to be given in advance. G max, maxima gain also from the gain medium parameter. So in principle, if you know small g, by this formula you can calculate I average, then all the way to E0. So that's why in solving equations 1 prime and 2 prime, when you get small g, you can use this system of formulas to get the, what do you want, steady state amplitude, E0. Okay. Although it's a little bit indirect, more complicated, but it's still durable. Any question?